Hi, welcome to Physics 123. Today we're going to talk about pressure. What is pressure? The definition of pressure is force per unit area. All right? So pressure is related to force. Why does it matter? Why does pressure matter? Well, first of all, it matters a lot in fluids. If you look at a fluid like water in a lake or water in a glass, and you ask, what is the force a meter at a depth of a meter in that fluid, you'd say, I don't know. It depends on what the fluid's pushing on. All right, we'll talk more about that. You can calculate the forces acting on things from the pressures in the fluid, but the fluid doesn't have a force, it has a pressure. So pressure is important when we talk about fluids, but pressure is also useful in its own right. If I want to know how something accelerates, F equals ma, right? So if I want to know how something accelerates, it's the force I care about. But sometimes I care about things other than acceleration. For example, you might be concerned about how much pain you will feel. If I were to lean against your shoulder, that would probably not cause a lot of pain, if I were leaning with my palm. But if instead I were grasping a knife and leaning on you with the point of a knife, that would probably hurt a lot, all right? So it's not the force that causes you the pain. It's not the force that causes the knife to break your skin. It's the pressure. Same force, but it's over a smaller area. The blade of the knife has a smaller area than the palm of my hand, all right? So pressure matters in fluids. It also matters in other cases, depending on what you're looking for. Pressure has units of force per area, so newtons per meter squared. 1 Newton per meter squared is defined to be a Pascal. So the units of pressure in the SI system are pascals. Now, imagine I have some object that I'm holding underwater. Imagine I have a wooden toy block and I hold it underwater. And I want to know, what force does the water exert on this cube? Well, we know that the pressure is force per unit area, right? So we can just solve this and we say, oh, the force acting in my cube is just the pressure of the water times the area of my cube. And you might think that, but you would be wrong. And the reason is, force is a vector. And it turns out that the direction of the force is different on different parts of the cube. The water on this side of the cube is pushing the cube that way, but the water on this side of the cube is pushing the cube that way. All right? So when we add together the force due to pressure on the different sides of the cube, they're all pointing in different directions. So we can't just take the total area and multiply it by pressure and get the force. We need a directional version of this equation, all right? Because force is a vector. All right? Well, the force on any given side of the cube, it's going to be equal to the pressure times the area, but then it's going to have a direction. So what we like to do is we like to, in physics, sometimes talk about areas as vectors. So if I take the top of the cube, I can draw a vector, and that vector represents the area of the cube. The length of that vector is just equal to the traditional area that you would find for that side of the cube. All right? The length is equal to the area. The direction is normal to the surface, and traditionally we choose it to be pointing into the fluid. All right, so now I make vector and area. It has a magnitude which is equal to the area you're familiar with, and it has a direction which points out of the cube, or normal to the surface. Now, of course, pressure exerts a force inward on the surface, so when we use the vector version, we usually need a minus sign because of the way we usually define the area vector to be. All right? But what if I had an object that was like some weird blob or a sphere that doesn't have nice sides? Then it gets harder, right? Because I can't just say, oh, I'm going to take this much area and I'm going to make it be a vector pointing in some direction. Because as I look at, let's say I have a basketball underwater, every point on the basketball, its normal is pointing in a different direction. So what we have to do, our cube, we broke it up into 6 pieces that had well-defined normals, right? If I try and break up my basketball into some finite number of pieces, each one of those pieces is going to have curvature to it, and I can't define a normal, a direction for my area vector. But if I keep dividing them up until I have an infinite number of little infinitesimal pieces, in that limit, each piece will only point in one direction. Its area will only point in one direction. So if I were doing a sphere underwater, for example, what I'd have to do is I'd have to take each little piece of that sphere, divide it up into an infinite number of infinitesimal little pieces. Each of those pieces would have an infinitesimal area, dA, pointing in a given direction, and then I would calculate the force acting on a little area, and it would be an infinitesimal force. A tiny little force is equal to negative the pressure at the location of that little piece times the little infinitesimal area vector of that piece. So I can find the little infinitesimal piece of force acting on that infinitesimal piece of the basketball. To find the net force, I just integrate all of the little forces, right? An integral is just a sum of an infinite number of infinitesimal things, all right? So here's the vector version of this equation, and here is the differential version of that equation. Density. All right. Density is something we're going to use a lot this semester, so let's just define what I mean by density. In this class, we'll typically use a Greek letter rho to represent density, and density is just defined to be the mass per unit volume. If I put a glass of water in front of you and said, hey, go look up on the internet what the mass of the water is in this glass, you'd say, I can't. I mean, the mass of a glass of water is not a constant. It's not just something you can look up. It's not a property of the water. All right? It depends on how much you have. So what instead you would do is you'd look up the density of water online. Density is a property of the water. And then you would say, oh, my glass holds this much water, so the mass of water in this glass is the density of water times the volume of the water in the glass. All right? So density is just mass per unit volume. We're going to use that definition now to figure out what the pressure is at a given depth in a fluid. So imagine I have a fluid which is not flowing. Okay? It could be a lake. All right? So imagine I've got a lake, and I'm going to imagine that there is a column of water in that lake. All right? So there's this column, this cylinder of water in the lake. Well, I'm not just going to imagine it. It's really there, right? There's water everywhere in the lake. But what I'm going to do is I'm going to imagine, I'm just going to think of this cylinder of water as being separate from the rest of the lake. And I want to know how the rest of the lake pushes on this cylinder of water. And I'm going to use this little thought experiment to figure out what the pressure is here at the bottom of the cylinder, a distance h down. All right? Okay. Now, what do I know about the cylinder of water? Well, I said that the lake is not moving. It's still. The water is still. That means that this column is not accelerating. If it's not accelerating, that means there is no net force on it. All right? That means that every component of the net force must be zero. So let's first think about the water pushing on the sides. All right? We know that this column is not accelerating side to side. So that means that the force on this side must be canceled by the force due to pressure on that side. All right? This is not a rigorous derivation, but it gives us some intuition that basically tells us something which is true, that in a fluid which is not moving, the pressure at a given depth is the same everywhere. All right? So if I go down 1 meter into the water and measure the pressure here, if I go down 1 meter and measure the pressure here, if I go down 1 meter and measure the pressure here, go down 1 meter and measure the pressure here, I will get the same reading everywhere. So the pressure is the same at any given depth if the fluid is not moving. All right? And because of that, then, all of the forces on the sides trying to push my cylinder sideways cancel out. Okay, so that's the one thing we learned from this. Pressure at a given depth in a static fluid is constant. Now let's consider the vertical motion of my cylinder, i.e. there is no vertical motion of my cylinder, therefore there must be no force because there's no acceleration, so the vertical forces must also add to zero. So let's look at what forces we have in the vertical direction. At the top of my cylinder, the atmosphere is pushing down on it. What is the force due to the atmospheric pressure? It's pressure, atmospheric pressure, times area. At the bottom of my cylinder, the water, the rest of the lake, is pushing up on the cylinder. What force does it push up with? Well, it's just going to be the pressure at that location times the cross-sectional area. All right? That's the force of the water below pushing up on the cylinder. There's one more force. Gravity is pushing my cylinder downward with a force mg. All right? So the sum of the forces has to equal zero. But the sum of the forces is I've got the pressure at the bottom pushing upward, I've got the pressure at the top pushing downward, and I've got gravity, mg, pushing downward. All right? And I can easily solve this for the pressure at the bottom here. I'll just divide everything by A to get rid of that. Then I move this stuff to the other side, and I find that the pressure at the bottom of my cylinder is just going to be atmospheric pressure plus mg over the cross-sectional area, all right? And this sort of makes sense because if I look at the very top here, the pressure of my fluid should be the same as atmospheric pressure, right? If my cylinder has no depth, it contains no water, therefore it has no mass, and I just get P naught. As I go deeper and deeper, the cylinder above me holds more water, therefore it has more mass, and the pressure goes up. But what is the mass of my cylinder? Well, the mass of my cylinder is just the density of the fluid times the volume. And the volume is just the height of the cylinder times the cross-sectional area. So let's take this mass and plug it into this equation. We get P naught plus the mass is rho HA times G over A. And the A's cancel out, and we end up with this equation. The pressure at some depth is just going to be the pressure at the top, which is normally atmospheric pressure, plus rho GH. And there you have it. Now you could have looked this equation up in the book and skipped this tutorial, skipped this derivation, skipped the book's derivation, and just started plugging things in to solve your homework problems. Students that do that, however, are not good students. And they will make mistakes because they will not understand this equation the way you have. Once you've derived an expression, you understand it much better. All right? So for example, imagine I gave you a problem where the pressure above the lake wasn't atmospheric pressure. Maybe this is in like a building that's been pressurized, right? And you pull this equation and you say, oh, that's atmospheric pressure. You're not going to plug in one atmosphere because you know where that came from. That came from the pressure at the top of your column pushing down. So the student who just blindly plugs things into equations is going to get it wrong, and you're going to get it right. All right? Also, you know what every term means. I've had students on exams plug in pressures for densities because the Greek letter rho looks like a P. But, I mean, especially looks like a P with my bad handwriting. But even if I wrote this exactly like that pressure, you would know it's not a pressure because you know where it came from. You've seen the derivation. All right? So it's always a good idea to understand where your equations come from and not just use them blindly. Okay, now let's talk about absolute pressure versus gauge pressure. Everything we've discussed so far is absolute pressure. That's normally what we use when we're doing physics. But sometimes when you're doing practical things, you end up using something called gauge pressure, so you ought to know what it means. It turns out that a lot of pressure gauges don't measure absolute pressure. They measure the pressure relative to the air around them. So for example, if you have a bike tire and it's all floppy and you're going to fill it up with air with your bike pump. So here's your floppy bike tire, here's the valve stem, and you hook up your bike pump to this, and you're going to go and pump up your bike tire, and you look at the gauge, and the gauge reads 0 atmospheres, or 0 pounds per square inch. How could it read 0? If the air in my tire was at 0 pressure, that would mean there's no air in my tire. And the atmosphere surrounding it would be pushing it in and crushing it, and it would look like shrink wrap, right? It would be all squished together. But your bike tire isn't pushed together because there's 1 atmosphere of air in it. If you open the valve, air doesn't go rushing in or out because there's 1 atmosphere of air in your tire, in your floppy tire. So why does your gauge read 0? It's because your gauge doesn't read absolute pressure. It measures the pressure relative to the surrounding air. It reads gauge pressure. So what it reads is gauge pressure, which is absolute pressure minus 1 atmosphere. So gauge pressure is just the absolute pressure minus 1 atmosphere. So if my bike gauge, my pump gauge reads 0, that means there's 1 atmosphere in my tire. If it reads 1 atmosphere, it means there's 2 atmospheres, absolute pressure in my tire. Now you usually don't have to worry about this because when you look on the side of your bike tire and it says inflate to 40 to 60 psi, it's giving you gauge pressure, which is what your gauge reads. You don't think about it, you just pump it up until your gauge reads between 40 and 60 psi. But if you were doing a physics problem and you wanted to know how many molecules of air were in your tire, you need absolute pressure for that. So you better convert from gauge pressure by adding on an atmosphere. Okay? Now, a barometer. There's a lot of different ways to measure pressure. When you take Physics 245, we'll show you a bunch of them. But for this class, we're just going to teach you about one interesting way to measure pressure, because understanding it will help you understand fluids and pressure. And that device is called a barometer. Here's how a barometer works. I fill a bucket with some fluid. I fill some pan or something with some fluid. All right? And it's open on the top. Okay? Now, the pressure everywhere along the surface of this fluid is atmospheric pressure, right? Because they're all at the same level. Usually, traditionally, people have used mercury for barometers because it has a very high density. Okay? Now, to make a barometer, I have this pan. I'm going to get a tube that's closed at one end. I'm going to fill it with my fluid. Say it's mercury. Okay? Then I'm going to put my thumb over the end. Before I do that, I'm going to put a glove on because, right, we don't like to touch mercury with our bare skin. All right? Then I'm going to take my gloved hand and stick the tube into the pool of mercury. All right? So here's the open end here. I've got my thumb on it. I'm going to take my thumb off, take my hand out. Now there's this tube of mercury. What does it want to do? Gravity pulls it downward, so it comes downward. All right? But it's not going to come all the way down. Why not? Well, because the pressure right here, pushing up on it, it's the same pressure as over here, the pressure of the atmosphere. Okay? So if there's some air or gas around my barometer creating a pressure P here, the pressure here at that same level is also going to be P. So my mercury in this column is going to be pushed up by a force P times the area. Now what's up here? What's the pressure up here? Well, for all practical purposes, this is a vacuum. Maybe a little mercury vapor up there, but mostly nothing. All right? So there is no force due to pressure up here. But there is a force due to gravity, right? mg. All right? And remember, m is just density of our mercury times the cross-sectional area times the height of our column of mercury. All right? So I do the same thing. My column of mercury is not changing. There must be no forces. So when I add my forces, I must get 0. And my forces are pressure times area upward minus rho A H G downward. All right? This is a rho, not a P. Since I have a 0 over here, I can just divide the A out of both sides. I can solve this for H, and what do I find? The height of my mercury column is pressure divided by rho G. There you go. Okay? You can check the units on it and make sure that I didn't make any mistakes. I'm going to just brush through this, but if we look at it, what does it tell you? The height of this mercury column tells you the pressure pushing down on the surface. So if you have a barometer and a weather system is coming through and the atmospheric pressure drops, the pressure of the atmosphere drops, the height of your barometer will drop. And you can use the height of that column of mercury to figure out what the pressure is. That's how a barometer works. Okay, now one last little thing. I'm going to show you how to use ideas of pressure to figure out the mass of the entire atmosphere surrounding the Earth. All right, so the idea is I've got this atmosphere and it's surrounding the Earth, right? And the Earth is holding it up. How much weight is the Earth holding up? How much atmosphere is there? Well, whatever the Earth pushes on the atmosphere pushes back with an equal and opposite force, right? So all I have to do is figure out what the force of the atmosphere is on the Earth, and that'll tell me how much the Earth is pushing up in the atmosphere. It'll tell me the weight of the atmosphere. All right? Well, how much is the atmosphere pushing on the Earth? Well, once again, I've got a sphere, but luckily, all right, we don't care about the net force on the Earth. We want to know kind of the pressure pushing everywhere, pushing inward on the Earth. All right? Okay. So the pressure at every point, if I take any little piece of the Earth, the force is always going to be downward, all right? And the pressure is going to be atmospheric pressure. Well, atmospheric pressure is a loaded term, all right? There's this thing we call 1 atmosphere, all right? That's a constant. But that's not what the pressure is in the room around you, right? The pressure depends on temperature, it depends on your altitude, depends on whether there's a storm system coming through, and so forth, all right? But this thing we call 1 atmosphere is sort of an average. It's a rough average of the pressure at sea level around the Earth. All right, so we're just going to do kind of a hand-waving thing and assume that the pressure is more or less 1 atmosphere all around the Earth. All right, and then I just have to say, well, each little piece of the Earth, all right, is holding up a wedge of the atmosphere. And how much weight is in that wedge? Well, it's just pressure. The weight is just the pressure times the area, right? So if I take atmospheric pressure times the total area of the Earth, adding up all these wedges, that will give me the weight of the atmosphere. All right? What is the area of the Earth? Well, area is just 4 pi radius of the Earth squared. So if you know the radius of the Earth, and if you know atmospheric pressure, you can find the weight of the atmosphere. Anyway,